Rafael this morning, and it's from pixels to planets, the process of validating transiting exoplanets.
All right. Well, thanks all for being here. I'm really excited to be able to talk to you today. And I'm also particularly excited to be able to kind of get into the guts of how we go from the Kepler pixels, the images we see on them, to detected planets. I don't usually get to talk about this much when I give talks because we skip to the science, but today we're going to go through what I think is really fun. So over the course of the next 25 minutes, I'm going to go through the process of going from pixels to validated or confirmed planets. And there are a couple of milestones or steps along the way, and I'll go through each of these and I'll explain what they all mean in turn. I'm mostly going to focus on data from the K2 mission. That's just an arbitrary choice on my part. I'm familiar with K2. I like K2 a lot. What K2 is, if you're not familiar, is Kepler was launched in 2009 with 4 reaction wheels. These are small gyroscope-like devices that spin to keep the spacecraft very finely tuned and finely pointed at one part of the sky. But after about 4 years of the mission, 2 of them failed, which meant that Kepler was no longer to keep itself pointed at its original field. Instead, it has to look at different parts of the sky, which are not as well characterized as the original Kepler field. And it wobbles a little bit, which introduces fun systematic errors into the data. So I'll briefly go over that a little bit as well. So Kepler looks now in the K2 mission at fields in the sky for about 80 days at a time. And it takes images every 30 minutes of many, many stars, 20,000 to 30,000. This is one of those stars. So you can see it's kind of wobbling back and forth a little bit. Every frame here is one of those 30-minute exposures. The way we take these images and turn them into brightness measurements is we simply choose our favorite pixels. I like those. And we're going to count up how many electrons are being recorded off of those pixels every time for the entirety of the observation. This is K2, so you can still see that there's some light that's moving back and forth, and there's some light that's falling inside and outside of those pixels. And that introduces some issues. So when you make these brightness measurements, you get something that looks like this in K2. Now, you've been seeing Kepler light curves all day, and there we go. You're used to seeing these really beautiful tight lines showing the brightness measurements. They're just like beads on a string lining up right in front of another. Kepler data is beautiful, and this is not necessarily all that beautiful. You can see these jagged motions in the light curve. This is caused by the unstable pointing. But if you correct for that, you can get something that looks more like Kepler. But the process of doing this isn't always perfect, and I'll come back to this later in the talk. So the next step in the process, after you've removed systematics and produced your brightness time series, which we call light curve, is you have to get rid of some of the low frequency trends. So this light curve here shows a rise upwards as the time goes on. These rises can be caused by instrumental effects, but they can also be caused by things like star spots. So imagine you have a star that's rotating. This is actually a real image of a star, which is really cool, I thought. And occasionally you'll see a dark spot that goes along in front. If you measure the total brightness of the star as it rotates, when that dark spot comes across, the total brightness should be lower. So you'll be in one of these valleys here. And when there are no dark spots, you'll be at one of the peaks. And when you do this over and over again, you trace out this quasi-sinusoidal curve. Raphael mentioned this earlier in her talk. This is not helpful for us for finding planets, so we can just get rid of it. And when we do that, we get something that looks like this. So this is your flattened light curve, which is ready for transit detection. One of the main ways we do this is by calculating periodograms, which Raphael also very nicely introduced earlier today. What this is a box least squares periodogram, like what Raphael was describing. We basically do a brute force search of every possible orbital period that you might find the planet at, and every possible duration for that planet transit. Could be 1 hour, could be 1.1 hours, 1.2 hours, etc. It could be at any possible orbital phase. The transit could be happening at any time. So you do a search over all of those possible planet orbits. And occasionally, you'll get something in your light curve that sticks out. And if you see a peak in your periodogram that reaches above some threshold, you can call that a detection. And in particular, you can call it a threshold crossing event. This is a zoom in of that particular detection in that light curve. It's pretty weak. There's a good bit of scatter here, but it does seem like there is a dip right here. And it seems like it recovers afterwards. So it looks like it could be a planet transit. And as I was saying, I would now consider this to be a threshold crossing event. And I've made this orange because this is one of those things that we had on the first slide that I was going to explain to you. So a threshold crossing event is any possible transit signal that has a period, time of transit, and a duration that's in a light curve strong enough for a transit search to identify. And the threshold at which you identify a signal is something that's left up to us, whoever designs the transit search algorithm. In this case, for K2 data, I use a fairly conservative signal to noise of 9 cut. If the strength of that signal is not 9 sigma or greater, I don't even think it's worth looking at, because in K2 data, there's a lot of residual noise from systematic errors caused by the motion of the spacecraft. So now that you can find one threshold crossing event, you can find thousands. So that's what we do. We search every single light curve observed by Kepler or observed by K2 during a particular time period. And we find lots and lots of threshold crossing events. Most of these are not planets. As Raphael mentioned earlier, in Kepler, only about 15% of the TCEs, the threshold crossing events, ended up turning into planets, even though most of the candidates, which Tim described, actually are planets, most likely. So in this case, this is the tools that I use personally to decide whether a given signal is an instrumental artifact or an eclipsing binary, or maybe a decent planet candidate. So this is the light curve without any systematic or without any low frequency variability removed. This is with low frequency variable removed. And these are the Boxley squared periodograms. And over here, you can see a phase folded light curve of the transit signal. And I'll show you the way I have over the past 4 years looked through these signals and decided if they're planets or not. There's a letter up here that starts off as U, that means undispositioned, and I change it with a keyboard stroke to J, most likely, for junk, because it's probably nothing. Occasionally, we'll get lucky and find one that's a candidate, which I will call C, maybe in a few seconds here. There we go. And then occasionally I'll find one that I call an E for eclipsing binary. This takes a long time. Like, I'm going pretty fast through this, right? I'm probably averaging, less than 1 per second. I can end up doing, on average, about 1,000 of these an hour, but it still takes a long time if you have several thousand that come through every 3 months. So this is the way things used to be. And right now I have a student named Anne Dattilo. She is a rising senior who will be applying to grad school next year, so keep your eye out for her. She is working on doing this automatically and taking a job like this, which I was able to do in a couple of hours, and she can do it with 98% accuracy on about 3,000 signals in 20 seconds. So I really wish I had this 4 years ago, but better late than never. I'll just let it finish. All right, there we go. So now that we have very quickly gone through all of these candidates, we can apply more stringent vetting tests to them to try to rule out scenarios like Raphael was showing earlier in her vetting diagnostics from the Kepler mission, such as eclipsing binaries with secondary eclipses or things coming from different parts of the sky. I'm only showing you a portion of the vetting diagnostics we use. In general, the things to look at are whether the transit appears consistent. These are all different individual transits. If one of them is really weird or wonky, then it might be an instrumental systematic. If there's a difference in the depth between the even transits and the odd transits, it could be an eclipsing binary orbiting at twice the period, where the even transits are the primary eclipses and the odd transits are the secondary eclipses. And if you see something right here that is at the right phase for it to be a secondary eclipse, this might be an eclipsing binary. This planet candidate looks pretty good. So we can assign it the category planet candidate, which is a threshold crossing event that passed both triage, the very rapid C, J, 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 C that classification that I did, and also passed this additional, more detailed vetting. So now I'm going to go into a different system here. This is a 6-candidate system, which was published by Joey, who was sitting over here. There he is, just Joey. A couple of weeks back on arXiv. And I'm going to use this system as an example of the kind of things that we have to do in order to determine if something is a planet candidate or a false positive. We're going to consider a couple different scenarios. You've seen images like these before. We want to decide now if each of these signals is a real planet, or if it's an eclipsing binary nearby, or if it's an eclipsing binary on that star itself. And then case D, the other case, whether it's an instrumental artifact. This is a tricky one, and this is something that our community has not yet robustly figured out a way to do. For now, we use some simple rules, which I'll show you. You may have read on arXiv, or not arXiv, on Astrobytes about the system. So if you're interested, you can check out Joey's work there. So I'll give you a quick overview of the system. There are two sub-Neptune-sized planets that are detected, candidate planets, that are detected at very high signal noise, about 110 sigma, near a mean motion resonance. So what that means is that this period here, 14 days, 14.7 days, is very close to a period ratio that is an integer, 4 to 3, with this planet here, which is at 19.5 days. These two planets, therefore, could be like those that Dan was showing earlier today, which show transit timing variations. These are very strong detections. There's another planet, which is a little bit of an oddball. So this is an ultra short period planet. The year on this planet is only about 18 hours, 0.66 days, and it's a small planet. It's only about a 120 part per million transit depth. This is an unusual one, especially because the duration of the planet is very short. That means it's a little bit tricky to confirm or validate using the Bayesian tools that Tim was talking about earlier, because we don't a priori expect for many planets to have a transit duration like this. So we'll have to do some more robust follow-up observations in order to validate this planet. There is one Mars-sized planet candidate, which we've detected at about 10 sigma confidence in a longer period orbit, a period of about 7.8 days. There's a couple other weaker ones. This is another Mars-sized candidate in a 6-day period. And then finally, there's a sub-Earth-sized candidate in a 56-day period, which, if it's real, would be in the habitable zone of this low-mass star. So this is an intriguing planetary system. And Joey and our team were really interested in trying to figure out a way to confirm whether these planets were there, especially this one here with the very short duration. So we started collecting follow-up observations. Tim was talking about how in many cases we don't need follow-up observations anymore, but it's always good to have the information. And you can always add that information into your validation procedures using things like Vespa and Blender. So what we did is we used the Palomar 200-inch telescope with the triple spec spectrograph to obtain a spectrum of the host star. This spectrum convinced us that the star was a dwarf star and not a giant star. And that made it easier for us to interpret these small dips as being caused by small planets, as opposed to smaller objects transiting a larger star causing very large dips, which might not necessarily be planetary. We also observed it with the 1.5 meter telescope at Mount Hopkins. We used the high resolution optical spectrograph there to very carefully measure the speed of the star, to measure the radial velocities. Now, these radial velocities we got here are not precise enough to actually detect the planet. It would take much more telescope time and more larger and more sophisticated instruments to actually detect the motion of these very small planets. But what we were able to do is we were able to see if the star was moving by a lot, which would indicate that instead of a planet candidate, one of these signals might be caused by an eclipsing binary. In particular, that the star was being transited by another star, which would cause these very large radial velocity variations. So based on the combination of these two follow-up observations, we were able to very conclusively rule out the possibility that this signal, or one of the signals, was caused by an eclipsing binary. We also looked at images that have been taken over the course of the last 70 years almost. So these are observations from the Palomar Observatory Sky Survey, which were taken in 1952. That's really cool, as we can see in some cases, when we're lucky, that stars may have moved due to their proper motion over the decades since then. So in this case, you can see that the present day location of the star, which is shown by this red cross, is on the outskirts of the image of the star in 1952. So if there was some bright star right behind it that could be causing one of these transit signals, we probably would have seen it. We can see a little bit better in this blue image, which is a little bit tighter in focus. And then we also use modern imaging. This is from the Pan-STARRS data release. All of these images can be downloaded by anyone in this room publicly for free from the MAST website. What's interesting about the Pan-STARRS images is that they are much deeper. They can detect fainter things. And you may not be able to see it on this projector, but there is a very faint star right here that's almost inside of the photometric aperture. So that's a danger sign, but it's not a terrible sign. If there is indeed a star nearby, it doesn't mean that there aren't planets around this star, but it makes it harder for us to assure ourselves that there aren't. There are. One of those words. So one of the ways we tried to rule out the possibility that this star was causing some of the transits is we chose a different set of pixels from Kepler to extract the light curve from. So if we use a slightly smaller aperture and exclude this region of sky, we can show that we still detect the signals of most of these planets in the smaller aperture, which means that they can't be caused by this star here. So that gave us some more confidence in most of them. We also obtained adaptive optics observations. We can use telescopes like the Keck Observatory to get nearly diffraction limited images despite the atmospheric turbulence that we have to contend with by using adaptive optics, which is where you have a deformable mirror that balances out the effects of atmospheric turbulence and sharpens the images to nearly the theoretical resolution of the telescope. So this image here is a very, very sharp image of that star. And there's really nothing going on here. There aren't any other stars detectable. There's some speckles, but those are instrumental artifacts as well. So to the best of our knowledge, there are no other stars anywhere nearby this host star that could be causing these planet signals falsely. Based on that, we can kind of rule out this scenario as well. It's still possible that closer to this star than the resolution of Keck, there is another star that's just totally blended. But the parameter space that we've ruled out with this image is very large. So I'll grade this out a little bit, but I won't conclusively rule out this scenario. And then finally, I want to talk about the instrumental false positives. And this is where our community, I think, has a lot of work still needs to be done. How do we know when something is caused by the telescope and not caused by something astrophysical? It's a tough question because it's really hard to model things that are caused by the telescope because we don't really know that much about our telescope. It turns out that sometimes it's easier to model the stars than it is to model a thing that's in space right near us and which used to be on Earth. So as a proxy for the likelihood of something being caused by an instrumental signal, we can use its strength. So we expect that Kepler data is going to be fairly good. It's not going to have much junk that's happening that's at really, really high signal to noise that happens repeatedly and mimics planets. But it might happen at low signal to noise. So of the 6 candidates that we were looking at, we decided to measure how strong the signals were. So as mentioned earlier, the 2 sub-Neptunes were both very strong signals. They have a significance of something like 110 sigma. And they look very clearly like sharp drops with little rounded bottoms. They're very clearly planet-like. The short period planet, the one with the very short duration, is also pretty strongly detected at about 13 sigma. And then the 7.8 day planet is detected at about 10 sigma. But below 10 sigma, we start to question the reliability of detections in Kepler data. So for out of caution, we decided not to validate these 2 candidates because we're not confident enough that they couldn't be caused by something like instrumental artifacts. And we don't really know what priors to use, and we don't really know how to model them in something like Vespa. So we're just going to leave them as candidates for now, and they'll have to be confirmed by some other telescope in the future. And this is one of the places that I hope that in the next few years, in the next few space missions, we'll be able to improve our understanding. Maybe one of you will be able to figure out how to accurately model instrumental artifacts in the false positive validation process. So we persevere. We make our we run Vespa on our candidates, we include the constraints that we've used from the radial velocity modeling, the lack of large radial velocity variations, and from the adaptive optics imaging and from the stellar characterization. And we calculate that the probability that these planets are actually false positives is quite low. And it gets better than that, actually, because it turns out that, as Dan mentioned earlier this morning, planets that come in groups tend to be real more often than planets that come by themselves. So here's the reasoning behind that. Imagine that you have a population of false positives that are scattered throughout the Kepler detector. These are eclipsing binaries. They don't have anything to do with the particular stars that they are found near. They're just scattered about randomly because we don't expect them to be clustered together on the sky. However, if we find planets that are all lined up and they all have inclinations that are very close to edge on, kind of like the ones in our own solar system, we might expect to see many different signals all transiting the same star. And that's in fact what we do see with Kepler. We see that there are a lot of false positives that are scattered about by themselves, but that there are planets that come clustered together all around the same star. And there are so many more of these planets that are clustered together than there are false positives that statistical analyses by people like Jack Lissauer have shown that planet candidates in multi-systems are 20 to 50 times more likely to be real than planets in single systems or than candidates in single systems. So what that means is we can take the probability that Vespa spits out here, this 1 in 2,000 false positive probability, we can divide that by 30 to 50 again, which means that it's easy for us to say with some confidence level that these candidates are all probably planets. And by that is what we're talking about when we say validated planets. And to go back to this discussion we had a little earlier about the difference between validated planets and confirmed planets, I want to show an example, or a couple of examples, one of them from this system. So these two sub-Neptune-sized planets here, these were validated. All of the ones in blue here were validated, and these two remain candidates. We're able to confirm a couple of them by some other method of detection. We can either detect their mass using transit timing variations or radial velocities, or we can detect them in some other way, such as Doppler tomography, which confirms that there's something definitely going in front of the star, even if we can't measure its mass, but we can put an upper limit on it. So in the case of Joey's system, we're able to take these two planets and measure their transit times. And it turns out that when you do that, you can see that there's a slope on the transit time of planet D, and then a kick upwards, a slope upwards on the planet E transit times, and then a kick downwards. And this dotted line here corresponds to the conjunction of those two planets. That's the dynamical signature of two bodies interacting within the same system, like Dan was talking about earlier. So we actually consider these two planets to be confirmed and not just validated. And then I'll show one final plot, which is another way of validating or confirming planets. This is a transiting planet discovered by the MERTH survey, and this is the radial velocity confirmation signal. You can tell that Raphael made this plot because it's purple. All of Raphael's plots are purple. Fun fact. And you can clearly see the signal of this planet is detected. And because we've detected the signal in two different detection methods, and they agree, they're the same period, et cetera, we can be very confident that this is indeed a real exoplanet. So I'll put up my map from pixels to planets again. I won't read this all aloud to you, but I'll leave it up during questions. Thank you very much.
Thanks very much, Andrew. So questions? See one hand here.
It is a neural network. Oh, the question was, how does the automated triage code work? So it is a neural network which uses as input the light curve, the phase folded light curve of each candidate. It doesn't use anything else about the star, et cetera.
Any more questions? Yep.
There are lots of different ways of doing this. I use a basis spline, which is basically piecewise stitched together polynomials that have some continuity rules. It's a nice way of doing it. There are other people who like to use Gaussian processes or median filters and stuff like that.
Any questions on this side? Any more questions? Yep.
Yeah, we had a test sample or a training set, which was everything that over the last 4 years I said J or C or E on. So that work didn't go all to waste. And we used the atom optimizer to minimize the cross entropy objective function.
One final question. Nobody? Okay, let's thank Andrea again. Thank you.